In the last two lectures, we have discussed the distributions of bivariate random variables. So, we looked at how to derive the marginal distributions and the conditional distributions. We also discussed various characteristics of the joint distribution, such as the moments, product moments, covariance and the coefficient of correlation, and we also looked at some of the features of these characteristics. Today I will introduce a particular joint distribution. It is known as bivariate normal distribution. So, a continuous jointly distributed random variable x y is said to have bivariate normal distribution if it has the probability density function given by f x y equal to 1 by 2 pi sigma 1 sigma 2 root 1 minus rho square e to the power minus 1 by 2 1 minus rho square x minus mu 1 by sigma 1 square plus y minus mu 2 by sigma 2 square minus 2 rho x minus mu 1 by sigma 1 y minus mu 2 by sigma 2. Here the range of x, y, mu 1, mu 2 is the whole real line, and sigma 1, sigma 2 are positive, and rho is between minus 1 and plus 1. So, first of all we look at that what are the marginal distributions and the conditional distributions, and overall structure of this bivariate normal distribution we will like to study. Suppose we want to find out the marginal distribution of x. In that case, we need to integrate this joint distribution with respect to y. A closer examination of the density function reveals that in the exponent we have a term which is a term like which appear in the exponent of the normal distribution. So, if we want to integrate with respect to y, we can convert it into a density with respect to y. So, that suggests that we make a perfect square in y. So, we can factorize it as 1 by 2 pi sigma 1 sigma 2 root 1 minus rho square e to the power minus 1 by 2 1 minus rho square. So, here if we make a square in y, then we have y minus mu 2 by sigma 2 minus rho x minus mu 1 by sigma 1 whole square. Now, this square corresponds to this and the cross product term corresponds to this. So, that means I have added rho square into x minus mu 1 by sigma 1 whole square. So, if we subtract this, I will get the term as 1 minus rho square x minus mu 1 by sigma 1 square, which we can write as 1 by root 2 pi sigma 1 e to the power minus 1 by 2 x minus mu 1 by sigma 1 square and 1 by root 2 pi sigma 2 root 1 minus rho square e to the power minus 1 by 2 sigma 2 square 1 minus rho square y minus mu 2 minus rho sigma 2 x minus mu 1 by sigma 1. So, this I can write as plus and arrange it in the bracket square. You can see here that the first term is a normal density for x and the second term is a normal density for y. So, if we want to find out the marginal distribution of x, we can integrate this with respect to y and we notice here that this entire term denotes a distribution which is normal with mean mu 2 plus rho sigma 2 x minus mu 1 by sigma 1 and variance sigma 2 square into 1 minus rho square. So, if we integrate with respect to y, this term will give us unity and we will get only this term. So, integration with respect to y gives f x x equal to 1 by root 2 pi sigma 1 e to the power minus 1 by 2 x minus mu 1 by sigma 1 square. That is, the marginal distribution of x is normal mu 1 sigma 1 square. In a similar way, we can split this term when we want to integrate with respect to x, then I make it as a perfect square in x. So, we will write x minus mu 1 by sigma 1 minus rho y minus mu 2 by sigma 2. So, another way of writing is another representation of f x y can be one by 2 pi sigma 1 sigma 2 root 1 minus rho square e to the power minus 1 by 2 1 minus rho square, and now I make a square with respect to x. So, x minus mu 1 by sigma 1 minus rho y minus mu 2 by sigma 2 whole square. So, comparing with the joint density, we can see here that x minus mu 1 by sigma 1 whole square, that is coming here, and the cross product term is minus 2 rho x minus mu 1 by sigma 1 into y minus mu 2 by sigma 2, which is the term appearing here. So, we have added the term rho square y minus mu 2 by sigma 2 square. So, subtracting this, we get 1 minus rho square y minus mu 2 by sigma 2 whole square. So, we can write it as 1 by root 2 pi sigma 2 e to the power minus 1 by 2 y minus mu 2 by sigma 2 whole square 1 by root 2 pi sigma 1 root 1 minus rho square e to the power minus 1 by 2 sigma 1 square 1 minus rho square, and x minus mu 1 plus rho sigma 1 y minus mu 2 by sigma 2 whole square. So, notice here that the second term is a density of normal random variable with mean mu 1 plus rho sigma 1 into y minus mu 2 by sigma 2 and variance sigma 1 square into 1 minus rho square. So, if we integrate this joint density with respect to x, the term, this term integrates to 1 and we are left with a normal density. So, the marginal PDF of y is f y y, that is equal to 1 by root 2 pi sigma 2 e to the power minus 1 by 2 y minus mu 2 by sigma 2 square. That is, the marginal distribution of y is normal mu 2 sigma 2 square. So, we come across this interesting phenomena that if x y follow a joint bivariate normal distribution, then the marginal distributions of x is normal mu 1 sigma square and the marginal distribution of y is normal mu 2 sigma 2 square. That means, given a joint bivariate normal distribution, the marginal distributions are univariate normal. Now, we also calculate the conditional distributions of x given y and y given x. Now, if we look at the conditional distribution of x given y, then we have to divide the joint distribution of x y by the marginal distribution of y. Now, from this breakup we can see that this joint distribution, if we divide by the marginal of y, this term gets cancelled out and we are left with this particular term, which is nothing but the normal distribution. This proves that the conditional distribution of x given y is normal and the mean and the variance are specified here. So, we have the conditional probability density function of x given y is equal to y, that is obtained as the joint distribution divided by the marginal distribution of y. So, after simplification it is equal to 1 by root 2 pi sigma 1 root 1 minus rho square e to the power minus 1 by 2 sigma 1 square 1 minus rho square x minus mu 1 plus rho sigma 1 y minus mu 2 by sigma 2 whole square. That is, we can say that x given y is equal to y follows normal with mean mu 1 plus rho sigma 1 y minus mu 2 by sigma 2 and variance sigma 1 square into 1 minus rho square. In a similar way, notice here that the joint distribution of x y was earlier factorized like this, and if we divide by the marginal distribution of x, then this term gets cancelled out and we are left with this term, which is again a normal distribution with a certain mean and a certain variance. So, this proves that the conditional distribution of similarly the conditional PDF of y given x that is obtained as 1 by root 2 pi sigma 2 root 1 minus rho square e to the power minus 1 by 2 sigma 2 square 1 minus rho square y minus mu 2 plus rho sigma 2 x minus mu 1 by sigma 1 whole square. That is, y given x is equal to x follows normal with mean mu 2 plus rho sigma 2 x minus mu 1 by sigma 1 sigma 2 square 1 minus rho square. So, we conclude that if the joint distribution is bivariate normal, the marginals as well as the conditional distributions are univariate normal. Now, the converse of this is also true. If the conditionals and the marginals are univariate normal, the joint distribution will be bivariate normal. So, this is also a characterizing property of the bivariate normal distribution. We can state it as a theorem. If x y follows bivariate normal with some parameters, say mu 1, mu 2, sigma 1 square, sigma 2 square and rho, then the marginal and conditional distributions of x, y, x given y and y given x are all univariate normal. Conversely, if the marginal and conditional distributions are univariate normal, then the joint distribution will be bivariate normal. So, this is quite useful in obtaining any probability related to marginal or the conditional distributions of the x and y, because we can make use of the standard normal distribution by making a suitable transformation. Any joint probability statement about bivariate normal distribution will need the tables of a standard bivariate normal distribution. By a standard bivariate normal distribution, we mean mu 1 is equal to 0, mu 2 is equal to 0, sigma 1 square and sigma 2 square is equal to 1, but rho will still be there, and therefore, several tables will be required with respect to which will be related to the joint probabilities of the bivariate normal distribution. So, since the marginal distributions are identified, we have expectation of x is equal to mu 1, variance of x is equal to sigma 1 square, expectation of y is equal to mu 2, and variance of y is equal to sigma 2 square. Now, we also consider the covariance term between x and y. So, the covariance term between x and y is expectation of x minus mu 1 into y minus mu 2. Now, this product, central product moment, can be calculated by the joint integration of the density function multiplied by this function. However, at this stage we introduce some formula for evaluation of the joint moments. If x and y have a joint distribution, then in general expectation of a function can be calculated in stages. We may calculate firstly the conditional and then with respect to marginal, or alternatively we may consider it as expectation of g x y given x, y given x, provided of course the expectations do exist. Let me give a rough sketch of the proof. Suppose x and y are continuous with joint PDF, say f x y. So, expectation of g x y we can express as integral g x y f x y x y. Suppose we keep the order of integration as dx dy. Then this we can express as g x y f x y divided by f y multiplied by f y dy. So, this quantity, inner quantity, is nothing but the expectation of g x y given y is equal to y multiplied by the density of y, which is nothing but expectation of expectation g x y given y. That means, the joint expectations can be calculated in stages, firstly with respect to a conditional distribution and then with respect to a marginal distribution in either order. So, if we make use of this, then expectation of x minus mu 1 into y minus mu 2, we can write it as x minus mu 1 into expectation of y minus mu 2 given x. So, inner expectation is the conditional expectation with respect to the distribution of y given x, and the outer is with respect to x. The conditional distribution of y given x was calculated to be a univariate normal distribution, and the mean was mu2 plus certain term. So, expectation of y given x will be mu2 plus rho sigma 2 x minus mu1 by sigma 1. Therefore, expectation of y minus mu2 given x will be equal to x minus mu1 rho sigma 2 by sigma 1 x minus mu1, which is nothing but rho sigma 2 by sigma 1 expectation of x minus mu1 square, which is sigma 1 square. So, it is rho sigma 1 sigma 2. So, we conclude that the covariance of the x y in a bivariate normal distribution is given by rho sigma 1 sigma 2. Therefore, we can calculate the coefficient of correlation between x y as covariance between x y divided by standard deviation of x, standard deviation of y, that is equal to rho sigma 1 sigma 2 by sigma 1 sigma 2, that is equal to rho. So, the parameter rho of a bivariate normal distribution denotes the correlation coefficient between the random variables x and y. Let us look at a problem here. The amount of rainfall recorded at a US weather station in January is a random variable x, and the amount of rainfall recorded in February at the same station is a random variable y. Suppose the distribution of x and y is observed to be a bivariate normal distribution with mean 6. So, the mean of random variable x is 6, the mean of random variable y is 4. So, suppose it is measured in inches because it is the amount of rainfall or centimeters. The variances are 1 and 0.25 and rho is equal to 0.1. We are interested to calculate what is the probability that x is less than or equal to 5, or what is the probability of y being less than or equal to 5 given that x is equal to 5. So, notice here probability of x less than or equal to 5 can be calculated from the marginal distribution of x, which is having mean 6 and variance unity. So, it is simply transformed to the standard normal probability as z less than or equal to 5 minus 6 by 1. Here z denotes the standard normal random variable. So, from 5 we have subtracted the mean of x and divided by the standard deviation, which is equivalent to the CDF value of a standard normal variate at -1, which we see from the tables of normal distribution as 0.1587. Suppose we are interested in the probability of y less than or equal to 5 given that in January the rainfall is 5. So, we need the conditional probability of y less than or equal to 5 given x equal to 5. For this we firstly calculate the conditional distribution of y given x equal to 5. Now, making use of the conditional distribution of y given x, which is given by normal with mean mu2 plus rho sigma 2 x minus mu1 by sigma 1. So, here mu2 is 4, rho is 0.1, sigma 2 is 0.5, sigma 1 is 1, and the point x is small x is 5. So, x is 5 and mu 1 is 6. So, this is the mean of the conditional distribution of y given x. So, after simplification this turns out to be 3.975. The variance of the conditional distribution is sigma 2 square into 1 minus rho square, which is 0.25 into 1 minus 0.01. So, it is evaluated to be 0.2475. So, the conditional probability of y less than or equal to 5 given x equal to 5 can be calculated from this distribution. So, we transform it to the standard normal distribution. So, it is z less than or equal to 5 minus 3.975 divided by square root of this, that is 0.4975. So, after simplification it turns out to be phi of 2.06, which is 0.9803, which is quite high probability, but that is understandable because in January there is more rain. So, since the variables are correlated, it is affecting the probability of y also. Let us take up another example of a similar nature. The life of a tube which is measured as random variable x1 and the filament diameter which is measured as a random variable x2. The life is measured in say hours and the diameter is measured in inches. They are distributed as a bivariate normal distribution with mu1 is equal to 2000 hours, mu2 is 0.1 inches, the sigma 1 square is 2500, sigma 2 square is 0.01 and the coefficient of correlation is 0.87. So, the manufacturer may use the filament diameter length which can be measured to estimate the life of the tube. So, if a filament diameter is 0.098, what is the probability that the tube will last 1950 hours? So, we are interested to calculate what is the probability of surviving till 1950 hours given that the diameter is 0.098 inches. For this we need the conditional distribution of x1 given x2 is equal to 0.098. So, we make use of the formula for the conditional distribution of x given y here. So, that is mu1 that is 2000 plus rho 0.87, sigma 1 is 50 divided by sigma 2 is 0.1, y minus mu2. So, y is the point at which we are conditioning, that is 0.098 minus mu2, that is 0.1. So, after simplification this turns out to be 2000.87 and the variance here is sigma 1 square into 1 minus rho square which is equal to 607.25. So, the conditional probability of x1 greater than 1950 given that x2 is equal to 0.098 can be calculated using this univariate normal distribution. So, after transformation to standard normal we get it as probability of z greater than minus 2.06 which is evaluated as 0.9803. So, likewise any probability statement related to the marginal distributions or the conditional distributions of x or y or x given y or y given x can be calculated using the univariate normal properties. We also look at the moment generating function of a bivariate normal distribution. So, the moment generating function of a bivariate normal distribution. So, it is defined as m x y s t that is equal to expectation of e to the power s x plus t y. Now, again you can see that this is some function g of x y. So, the joint expectation we can calculate easily in terms of conditional and the marginal expectations. So, we will use that, we can write it as expectation of expectation e to the power s x plus t y given, say in the previous one we have done the calculation using conditional distribution of x. So, we can use the conditional distribution of y here. Now, given y, this e to the power t y terms is fixed. So, we can separate it out and we are left with expectation of e to the power s x given y. Now, notice here that this inner expectation is nothing but the moment generating function of the conditional distribution of x given y. So, this is equal to expectation of e to the power t y into the moment generating function of the conditional distribution of x given y at the point s. Now, here the conditional distribution of x given y is univariate normal. We already know the form of the moment generating function of a univariate normal distribution. Suppose the normal mu sigma square distribution is there, then we have seen that the MGF is represented as e to the power mu t plus half sigma square t square. So, here the point is S in place of t, and x given y, the distribution has the parameters mu 1 plus rho sigma 1 y minus mu 2 by sigma 2 and sigma 1 square 1 minus rho square. So, we make use of this. So, this can be expressed as expectation of y e to the power t y e to the power mu 1 plus rho sigma 1 y minus mu 2 by sigma 2 into S plus half sigma 1 square 1 minus rho square S square. So, this is the value coming after substituting the value of the moment generating function of the conditional distribution of x given y, which is univariate normal, and therefore, the form is known to us. So, now here there are certain constant terms and we can separate it out, e to the power mu 1 s minus rho sigma 1 mu 2 by sigma 2 s plus half sigma 1 square 1 minus rho square s square. We have expectation of e to the power y t plus rho sigma 1 by sigma 2 s. So, we notice here that this is nothing but the moment generating function of y at the point t plus rho sigma 1 by sigma 2 s. So, this term is there. So, notice here that the distribution of y is again univariate normal with parameters mu 2 and sigma 2 square. Therefore, the moment generating function has a known form. In place of the point t, we substitute t plus rho sigma 1 by sigma 2 s. So, we get it as e to the power mu 1 s minus rho sigma 1 mu 2 by sigma 2 s plus half sigma 1 square 1 minus rho square s square e to the power mu 2 t plus rho sigma 1 by sigma 2 s plus, so I will write it as e to the power half sigma 2 square t plus rho sigma 1 by sigma 2 s whole square. So, we have e to the power mu 1 s plus mu 2 t, that is this term. Now, we note here minus rho by rho sigma 1 sigma by sigma 2 mu 2 s. This term is coming here also as a plus sign, plus rho sigma 1 by sigma 2 mu 2 s. So, this term gets cancelled with this term. Then we have half sigma 1 square s square and half sigma 2 square t square. Now, when we take a square here, it is becoming twice rho sigma 1 by sigma 2 s t. So, sigma 2 and sigma 2 square. So, you will get it as plus rho sigma 1 sigma 2 s t, and the square term here rho square sigma 1 square s square with a half here will get cancelled with minus half sigma 1 square rho square s square. So, we are left with this term as the MGF of the bivariate normal distribution. So, notice here that e to the power mu 1 s plus half sigma 1 s square denotes the MGF of the normal distribution with parameter mu 1 and sigma 1 square, that is the MGF of x. Similarly, e to the power mu 2 t plus half sigma square t square denotes the MGF of y. So, we have these terms and an additional term coming here. So, using this we can prove certain more properties regarding the bivariate normal distribution. Let x y follow a bivariate normal distribution with parameters mu 1, mu 2, sigma 1 square, sigma 2 square and rho. Then x and y are independent if and only if rho is equal to 0. Now, we already know that if x and y are independent, then correlation is 0. So, rho will be equal to 0 will be true. To prove the reverse, we make use of the joint MGF. So, x and y are independent. This is equivalent to the statement m x y s t is equal to m x s m y t for all s t. Now, this is equivalent to e to the power mu 1 s plus mu 2 t plus half sigma 1 square s square plus half sigma 2 square t square plus rho sigma 1 sigma 2 s t equal to e to the power mu 1 s plus half sigma 1 square s square e to the power mu 2 t plus half sigma 2 square t square. So, this is equivalent to the statement that rho is equal to 0. So, although in general correlation 0 does not imply independence, but in the case of bivariate normal distribution, independence and correlation is equal to 0 is equivalent. We prove another property of bivariate normal distribution using the moment generating function. X y follow a bivariate normal distribution with parameters mu 1 mu 2 sigma 1 square sigma 2 square rho if and only if a x plus b y follows a univariate normal distribution with parameters a mu 1 plus b mu 2 a square sigma 1 square plus b square sigma 2 square plus twice a b rho sigma 1 sigma 2 for all a b real. Of course, both a and b not simultaneously 0. This is a very strong property because it says that given that joint distribution is bivariate normal, any linear combination will be univariate normal. Conversely, given every linear combination is a univariate normal, the joint distribution will be bivariate normal. So, in order to prove this statement, let x y have bivariate normal distribution with the given parameters mu 1 mu 2 sigma 1 square sigma 2 square and rho. Let us write the random variable say q as a x plus b y. Then the moment generating function of q, that is equal to expectation of e to the power t q, that is equal to expectation of e to the power t a x plus b y, that is equal to expectation of e to the power a t x plus b t y. This is the joint MGF of x y at a t b t. Since x y has a joint bivariate normal distribution, the form of the joint MGF of x y at a t b t can be obtained by substituting S is equal to AT and T is equal to BT in the expression given just now. So, this becomes e to the power mu 1 AT plus mu 2 BT plus half sigma 1 square A square T square plus half sigma 2 square B square T square plus rho sigma 1 sigma 2 A B T square. So, after combining the coefficients, we get it as T A mu 1 plus B mu 2 plus half T square A square sigma 1 square plus B square sigma 2 square plus twice AB rho sigma 1 sigma 2. Now, this is nothing but the MGF of a normal distribution with the mean this term and variance this term. So, because of the uniqueness of the MGF, we prove that Ax plus By is having this particular normal distribution, which is the MGF of a normal A mu 1 plus B mu 2 and A square sigma 1 square plus B square sigma 2 square plus twice AB rho sigma 1 sigma 2 distribution. So, by the uniqueness property of the MGF, we conclude that Ax plus By has a normal distribution with given parameters. Now, conversely, assume that let Ax plus By have normal distribution with the desired setup. Now, consider the joint MGF of xy, that is M x y s t, that is expectation of e to the power s x plus t y. Now, notice here that this is nothing but a linear combination of x and y. We are assuming that every linear combination has a univariate normal distribution with desired parameters. So, this becomes nothing but the moment generating function of s x plus t y at the point 1, which is known to us, because the distribution of s x plus t y is assumed to be normal with mean s mu 1 plus t mu 2 and s square sigma 1 square plus t square sigma 2 square plus twice s t rho sigma 1 sigma 2. So, since the MGF of the normal distribution is known, we substitute this here and it becomes equal to e to the power s mu 1 plus t mu 2 plus half s square sigma 1 square plus half t square sigma 2 square plus s t rho sigma 1 sigma 2, which is the MGF of a bivariate normal distribution with the parameters mu 1 mu 2 sigma 1 square sigma 2 square and rho. So, once again the uniqueness of the MGF proves that x y must have a bivariate normal distribution. So, notice here that this joint MGF is extremely useful in proving certain characterization properties of the bivariate normal distribution. We also look at the generalization of the concept of joint distributions to more than 2. So, in general we may consider a k dimensional random variable. So, we call it random vectors in general. So, x is equal to x1, x2, xk. So, this is a k dimensional random vector. It is defined to be a measurable function from omega into rk, and of course, the function should be measurable. Now, you may have the random variables, some of the random variables xi as discrete, some of them as continuous. We may have some of them as mixtures. So, all types of possibilities of the type of the random variables are there. We may make use of the joint CDF. Joint CDF of x is defined as f x x as probability of x1 less than or equal to x1, xk less than or equal to xk, where this point x is equal to x1, x2, xk belongs to rk. Now, this function, as in the case of two variables, this is giving complete information about the types of random variables xi's are, and also the probability distributions of individual xi's are conditionals. For example, if I take limit as xi tending to minus infinity in any I, then this will be 0. If we take limit as say xi tending to plus infinity, then that will yield the CDF of all the variables except the ith one. We may also obtain the marginal distributions of only x1 or only x2 by taking the limits of all other variables tending to infinity. The function f(x) is continuous from right in each of its argument and also non decreasing. Making use of this joint CDF, we can define the concept of independence. x1, x2, xk are independently distributed if the joint CDF can be written as the product of individual CDFs for all x belonging to Rk. Now, we can take the particular cases, that is when all of the xi's are discrete or all of the xi's are continuous, because in that case we can define a joint probability mass function and joint probability density function respectively. So, let us take up these two cases. Let x1, x2, xk be discrete, that means all of the components are discrete. So, we have a probability mass function, that is probability of x1 is equal to x1 and so on, xk is equal to xk. It will satisfy the usual properties, that is it should be non-negative function, and if we sum over all possibilities of x1, x2, xk, it should add up to 1. So, this is the joint probability mass function. It will satisfy the properties that Px x is greater than or equal to 0, and the sum over all the components must be 1, where x is the set of values of x. The marginal distribution of any subset of x1, x2, xk can be obtained by summing over the remaining variables. For example, if we want the marginal distribution of x1, then we will sum over the joint PMF over x2, x3 up to xk. Suppose we want the marginal PMF of say xk minus 1 and xk, then we will sum over the variables x1, x2, xk minus 2. Likewise, we can define the conditional probability mass functions of any subset of x1, x2, xn given any other subset of x1, x2, xn. So, the conditional and marginal PMFs of any subsets of x1, x2, xk can be obtained from the joint PMF. In a similar way, we may talk about the case when all of the xi's are continuous. In this case, we will have a joint probability density function. And it will have the properties that the function is non-negative, the integral over the entire space must give 1. And if I take A to be any subset of the k dimensional Euclidean space, then probability of x belonging to A is where the integrand is integrated over the range A. Once again, the marginals or conditionals of any subset of x1, x2, xk can be obtained by integrating over the remaining variables. For example, if I want the marginal distribution of x1 and x3, then leaving only x1 and x3, we will integrate the joint distribution with respect to x2, x4, x5 and so on. Similarly, we may talk about say conditional distribution of x3, x5 given x2. So, that will require the joint distribution of x2, x3 and x5 and the marginal distribution of x2. We can define the joint moment generating function of x1, x2, xk as mxt, where t is the point t1, t2, tk as expectation of e to the power sigma ti xi I is equal to 1 to k. That is expectation of e to the power t prime x, where t prime denotes the transpose of the vector t. Using this, we can prove the theorems as in the case of bivariate that x1, x2, xk are independent if and only if the joint MGF is the product of the individual MGFs for all t. Similarly, if the random variables x1, x2, xk are independent, then the MGF of the sum is the product of the MGFs. Now, this is a very useful tool in evaluating the distributions of the sums of random variables. Given that certain random variables are independently distributed, if we are interested in the distribution of the sum, then we simply multiply the MGFs of the individuals and notice that what is the form of that. If it is identifiable with certain distribution, then we know the distribution of the sum without going through the usual procedure of transformations. From MGFs itself we can derive the joint MGF. Using this, we will show the additive properties of certain distributions in the next lecture, and we will also see some special joint distributions. So, today we will stop today's class here.